All right, which takes us to problem number 6. A crate of eggs is located in the middle of a flatbed of a pickup truck as the truck negotiates an unbanked curve in the road. The curve may be regarded as an arc of circle, radius 35 meters. If the coefficient of static friction between the crate and the truck is 0.6, how fast can the truck be moving without the crate sliding? So what is the very fastest we can go before that crate slips? You say, hey, what is the force that's preventing it from sliding? You're going to say, oh, well, that's friction opposes sliding. In particular, we're trying to keep it from slipping. This is static friction. Not only that, we are going to be at the very limit of static friction. We're the fastest we can go before it slips. And that's very good for us because it allows us to use the formula for static friction. All right, so here we go. Let's draw a quick sketch. Do you like left curves or left turns or right turns? I don't know. I'm going to draw it as a left turn. So look, there's our curve in the road. Here is that truck, that pickup truck. So like here's like, the bed of the truck. All right. Okay, and we have this crate sitting in the back of the truck. That's our system, is that crate. And hope it's a one-lane road because, we're driving right down the middle. So we are cruising along here, and we want to know what is the fastest that we can go without that crate sliding. So we're doing at that max speed, Vmax, right? Okay, so I want to do my force diagram for the crate. Now, in circular motion problems, typically, the direction that we want to, we talk about how sometimes it might be nice to do 2 diagrams, right? Sometimes we'll do that here. For this case, I'm going to do, this is like the top-down view as we're making that left turn. I'm going to do a rear view, looking from behind, so it's going away from me. When I draw the picture, it'll be going into the page. Here is that crate. All right. As it's making a left turn, I'm looking from behind. This is like a top-down. This is looking down the z-axis, and this is a rear view. Okay, which is going to be looking down the tangential axis. Alrighty, both of these diagrams, I'll be able to see the radial axis in it, which is kind of the point. You don't want to look down the radial axis. Okay, that radial direction is the direction that we know the acceleration centripetal. We have that cool equation for, and so we want to make use of the fact that we know that. We want to be able to see the radial axis in all our pictures. Okay, rear view, range forces. There is a gravitational force. Contact forces, what's touching the crate? Well, the floor of the truck here, right? Are they being pressed together? Yes, they are. So there's a normal force going up. Normal force on the crate by the truck bed. And then you say, once you have a normal force, you can ask yourself if there's a friction force. All right. Now, this is weird. Okay. Which direction is the friction force going? Well, it's opposing the slide, right? Here's what's happening. The truck is not going in a straight line. It is moving like that, right? You know what I mean? And so as it turns, right, if that crate stood still, it would start to skid, wouldn't it? Wouldn't it kind of slide in the truck bed as the truck starts to turn and it wants to keep going straight? There's a friction force keeping it from slipping to the right. That is a friction force pushing the crate to the left. That is the way the static friction goes. And on this picture, if this friction force, do we want the friction force pushing in the direction of motion, making it go faster? You want the friction force going against the motion, making it get slower? It can only go perpendicular to the velocity because we're not getting faster or slower. Must be COVID. Here we go. And so you say that force, I shouldn't joke about that. I apologize. That static friction force must be going inward toward the center. And that, my friends, is the force diagrams. Okay. And again, I've got my tangential axis and my radial here, right? I'm looking down the z-axis. Here, I have the z-axis and the radial, right? I'm looking along the tangential axis. Okay, these two pictures. Okay, so I got my top view, I got my rear view. Alrighty, this is looking down the z-axis view. Okay, there we go. All right, now I've got my force diagrams, my free body diagrams. I am ready to go to sigma F equals ma and solve these problems. Okay, we want to know the very fastest, right? You say, now where am I going to get speed? Well, that's going to come in the radial axis when I do centripetal acceleration. So every circular motion problem, pretty much, we are going to analyze the radial axis. I might not know anything else about how to solve the problem, but I can always go to drawing the force diagrams. That's a starting point. And then I can start doing sigma F equals ma for the axes, and that gives me some equations to start playing with. I can see where I'm at. So doing force diagrams, it is like, you know, it's like it gives you a point to start from. You're not supposed to necessarily see how the problem's going to shake out when you first read it. You figure it out as you go along. You kind of follow your nose through the problem. And like force diagrams and Newton's second law is like a good first step. All right, and it kind of gets you on your way. So here we go. Let's do the radial axis. All right, and so you say, okay, look at the radial axis, and I do sigma F equals ma. This is radial. I know the acceleration of the radial has to be centripetal toward the center. All right, and so I can say radial forces in minus out. You know what? There's only one force in the radial axis, static friction. I'm going to make it positive because left is positive? No, because in toward the center of the circle is positive, right? The center of the circle is that way. All right, so that's equal to m. Centripetal acceleration, I can substitute in speed squared over r if I wish, which I do. And you say, okay, I am trying to solve for the fastest I can go. V, look, that's the variable I want. I want that. That's what I want. I want to find that. Okay, do I know m, the mass of the crate? And you say, no. Do I know the radius of the turn? Yes. Okay, so I don't know this guy either, right? Do I know the static friction force? No. So there's too many variables. And so you say, all right. Okay, maybe static friction. Remember that static friction is any value up to a maximum. And you say, okay, well that I am at the max in this problem because I am at the very limit to what that friction force can pull with to keep it from slipping. So that's when it's equal to mu Sn. So I'm allowed to substitute mu n in here. And you say, okay, did that help at all? I'm trying to solve for V, right, that I don't know. I don't know M. You're like, okay, mu, they told me that's 0.6. Oh, so I got rid of the F, but I replaced it with another variable I don't know, N. You're like, was that a help? Well, yeah, I can find N. It shows up in another equation. Look, it's a force in the Z-axis, right? And so I can do a sum of the forces in the Z-axis. Sum of the forces in the Z is mass times acceleration in the Z. Hey, how fast is this crate accelerating up off the bed of the truck? It's not. So the acceleration in the Z is going to be 0. Equations with zeros in them are always make you happy. Hey, forces, so I'm going to call, I probably should have labeled my coordinate axes before I got started, shouldn't I? Yes, I should have. Okay, this is the radial, this is the tangential, this is the positive directions. And let's say here, this is the Z, and this is the radial. And positive directions here, because that way it's got to be positive for radial, right? Okay, and I just arbitrarily chose to call the direction of motion and up as positive. Anyway, moving onward. So when I go and I do my my forces from the diagram, it's going to be N minus mg is 0, right? And so look, N is just equal to mg. And I can take that, of course, and I can substitute. Whoa! In for N, okay, on this side. And so I'll have mu mg, that's okay. My color coding got messed up here. Anyway, equals mv squared over r. And you say, hey, look, every term has a m in it. And so that mass is going to drop right out of my calculation. Hooray! Right? And so now I got rearranging. I'm going to move the r over there, and I'll have Muger. Square root of Muger is v. And this is by the way, because I made this maximum, m's a constant, r is a constant, this is v max, because that's the maximum static, okay? And so that's what I'm trying to find is the maximum speed, okay? So because at this point when I substituted that in, I made this the max value. And so that has to be the max value, okay? And so that v max, right, I can plug in my values, 0.6 times 9.8 times a radius of, what was the radius in this one? 35 meter radius turn. It's a nice wide turn. Square root. Okay, punch that in my calculator. Square root of the quantity. Whoops. 0.6 times 9.8 times 35. Right? Bam. 14.35 about. So 14.35 meters per second is my maximum velocity to keep that crate of eggs from sliding in the back of the pickup truck. The end. All right. Lots of little things going on here. 2 diagrams, helpful, right? You can see, when you do this view, you can see which way the center of the circle is very clearly, so you know what the radial axis is. This one, we needed to see the z so we could figure out the normal force to find the friction. Again, with friction forces, you always end up having to look at 2 axes because you got to find the normal force that's pressing the surfaces together to figure out how big the friction force in the other axis is along the surface. But yeah, that's it. That's the idea. We didn't have to analyze the tangential. Okay, for this problem, didn't need it. Didn't need it. Nope. Okay, there we go.